I'm going to introduce Semantic CVO, a new framework for registering semantic point clouds from stereo and RGB-D cameras. Range sensors, like stereo and RGB-D cameras, can be found in many modern autonomous robots. They're heavily used in localization and mapping algorithms to generate the poses at different timestamps. These range sensors can provide rich information, not only the geometric measurements, but also the color or even semantic information as well. The main question is, how do we combine the semantic and geometric information into a unified model that works better in practice? Especially, we are interested in the point cloud registration problem, which is the building block of many 3D computer vision and SLAM systems. The point cloud registration problem estimates the relative pose between two successive point clouds. That it is a hard problem because the observations could be pretty noisy. The 2 point clouds might just partially overlap. The scene is textureless. There might be different densities of the observations, and there might be some dynamic objects in the scene. Existing methods usually formulate the problem as some optimization problem. Different methods might have different representations of the point clouds, and then the cost functions are defined accordingly. Iterative closest point is a very famous point cloud registration problem. It relies on one-to-one data correspondence and represents the point cloud as a discrete set of points. The cost function is minimizing the pairwise geometric residuals. It is possible to incorporate extra color or intensity information by adding the regularizers for these colors. UMich-CURLY differs from other traditional ICP in that it treats the data correspondence as a hidden variable and then use EM algorithms to infer it in the middle. However, parameterizing the correspondence could take a lot of time. Normal distribution transform is another class of point cloud registration methods that works very well in practice. It represents the point clouds as voxels of Gaussian distributions, and the cost function is basically the maximum likelihood, fitting the observations of the second point cloud into the distribution of the first point cloud. However, efficient and accurate discretization is challenging. In this work, we propose a new point cloud registration method that is continuous, that doesn't rely on one-to-one data correspondence, and it is easily extendable to non-geometric information like color or semantics. Let's go back to our basic problem. We want to find a good representation for the 2 point clouds x and z, and we want to define a suitable cost function for them. Finally, we want it to be data association free. The 2 point clouds representation should include both the geometric and color semantic observations. Here's an example from the Kitty dataset. Let's pick a single point xi from the stereo observation. This xi has the color pixel, which is basically a 3-dimensional vector. It also has a corresponding semantic observation from some neural network, and it has a different dimension than the color. We combine them with the tensor product. And this is what we call the hierarchical semantic representation for a single point x, or we can call it as a label. So this label will encode the non-geometric information for a single point. Besides the hierarchical semantic information, we also encode the geometric information with a square exponential kernel. This kernel will have larger values for points that are close and has very, very small value for points that are far away. So we do this for all the points, and we obtain a function representation for the entire point cloud, fx. It is essentially a weighted sum of geometric kernels, while the weights are the labels. Now that we have the continuous function representation for the point clouds, we want to define a class for it. We want the class to avoid the explicit hard data association. The class function should measure the alignment between the two point clouds. For vectors in the inner product space, we can use the angle between them as a measure of alignment, and this also applies to point cloud functions. So here we define the cost function as the inner product of the two functions of the point clouds. The nice thing about this cost function is that it avoids explicit hard data association, and we are actually aligning the two functions instead of two pairs of points. After some math manipulation, we arrive at the double sum of geometric kernels, where the weights of the geometric kernels are the visual features. So this objective function will contain the information from both the geometric and non-geometric information. We want to perform the gradient ascent to maximize this objective function. A nice byproduct of this cost function is that, similar to the normal vectors, we can use the cosine angle between these two functions to measure the alignment of these two point clouds. Below is an example from the Kitty dataset where we change the homogeneous transformation by rotating and translating them, and we can see that the cosine value will change accordingly, and when the rotational angle is 0 and the translational distance is 0, this indicator of alignment will have larger values. So to sum up, we will propose a framework for registering hierarchical semantic point clouds. The point clouds are represented as continuous functions that takes the geometric and non-geometric information into consideration. And the registration problem is formulated by maximizing the two functions. In our practical implementation, the computation for the double sum might be costly. So we downsample the points with OpenCV fast point cloud selector. Also, we compute each element in this double sum in GPU in parallel in order to speed things up. Here are our experimental results. We evaluate on both an outdoor and indoor dataset. Kitty is an outdoor dataset that provides the color serial cameras. It has multiple sequences with ground truth, and error was evaluated by translation and rotational drip per 100, 200 until 800 meters. The Kitty stereo point clouds are computed via IEEE. As you can see the picture on the right, it provides stereo point clouds, but there are still noise from the color and geometric. And also, we get the semantic observations from the neural network, but still, there are some noise visible. Here is an example of aligning two point clouds. The first one is in orange and the second one is in blue. Here's another example in the Kitty dataset sequence 3, and in this example we want to align the entire sequence frame to frame. And the curve in the middle, in green, is the accumulated trajectory from our frame-to-frame registration. The point clouds are stacked together based on the transformation from our algorithm. This algorithm will take both the semantics and color information, as you can see on the top. This is a close look at the stacked point clouds. Still, the green trajectory is in the middle. And we can see that the roads are pretty clear. This is a qualitative comparison between the proposed methods and several baselines. The ground truth is the black dashed curve. The three solid curves are the proposed methods, and the dot dashed curve are the baselines. This is another sequence with similar comparisons. Still, the black dashed curve is the ground truth. The solid curves are the proposed methods, and the dot dashed curve are the baselines. This picture shows that the proposed methods have lower drift at both at lower and higher speeds, while some baselines might have higher drift when the speed goes fast. So this is the quantitative result. When using both color and semantic information, the proposed method will have the lowest translational and rotational drift. Tzu-Yuan dataset is an indoor dataset that used RGB-D cameras. This sequence could be challenging because it includes some non-structured, non-textured environments, and the observations could be pretty blurry. Here's an example in a structured but non-textured scene. Still, our trajectory from frame-to-frame registration is highlighted in green, and then we stack the point cloud based on the our registration result. As you can see in the map, the scene is pretty featureless, and it can be challenging for traditional registration methods. In the quantitative results, we can show that our geometric results are comparable or better than geometric baselines, and our color results are comparable or even better than the color baselines. So, to sum up, we propose a novel point cloud registration method that represents hierarchical point clouds as continuous functions. We introduced a new way to measure the alignment, and we demonstrate comparable or better performance versus baselines. The code is released open source. Any questions is welcome.